Allora, io direi di cominciare, sono le 3:10. Il 4° problema di Hilbert è la nozione di semplicità delle dimostrazioni, in inglese perché la presenza di colleghi di altri paesi. Grazie Matteo di darci questo seminario. Poi, sarà seguito dalla discussione, potete intervenire direttamente attivando i vostri microfoni.
Okay, so English. So thanks for the invitation, and so this seminar will be, as the name suggests, about the Hilbert problem, and let's say I will present it under the point of view of what I do in research, and as you can see, my affiliation is at the Security and Trust of Software System. So for who doesn't know, I come from mathematics. I did logic, and now I sneak inside a team which mostly deal about the problem of security in software. So let's say that the seminar is a self-justification on why I'm there. So let's start our story, and I think everybody knows the Hilbert problems. And so David Hilbert was a famous mathematician at the Second International Congress of Mathematicians in 1919. So instead of going as usual, people goes to a conference of mathematics presenting some solution. Hilbert came and presented some problem, which the idea to inspire the work of the mathematicians for the last century. And so just to give an idea of which kind of problem is present, I will talk about the first three. So the first one is the also renamed problem of the continuum hypothesis. And the question is if it's possible to map every subset of real number into, there is a bijection between natural numbers and a subset of real numbers. And the answer was, let's say, had a solution, and the question is independent from the set theory, and it has been proven the first part by Gödel in the 40s and the second part by Cohen in the 60s. So as you see that the questions are not so trivial sometimes. The third problem is, I choose them because it's particularly easy to explain, and the question is, if you take one polyhedra, which is a three-dimensional object with all faces which are plane, is it possible to cut using planes and rebuild another shape with the same volume? And here the representation is just for a two-dimensional object because of the slide are two-dimensional. And for example, this problem has been answered the same year. And the answer is essentially you cannot take a cube and cut with a knife and build a pyramid with the same pieces. However, the question has a pretty simple solution for polyhedra, and where you asked to cut the polyhedra with planes. However, if we consider more border setting, you don't ask to be a polyhedra, you have the famous Banach-Tarski paradox, in which you can take a sphere and using axiom of choice, and you can build two spheres of the same volume. So you see that this setting was really narrow. And just to have an idea, the solution of the problem for polyhedra comes from the definition of some invariance, which, as you know, is some mathematical object you associate to other mathematical object in such a way when you do some transformation to the object, the invariant is invariant, so it doesn't change. And the third problem which I present is the second problem, and the reason why, because as computer scientists, we can see the second problem as the sparkle of the computer science, and it was pretty simple. The question is it possible to prove that arithmetic is consistent? And the answer took a lot of time, but we know from the Gödel theorem that if we have a theory which expresses arithmetic is incomplete, and we know that if you have a theory in which you can express arithmetic, then you cannot prove the theory in itself. And another, the complete answer, if you want, comes from Gens and the 36, when they say, okay, you can prove the consistency of arithmetics, but you need the induction over epsilon 0. And why I tell that this problem is a sparkle of computer science is because the proof of Gödel had the idea of encoding a mathematical theory by using arithmetic, so by using numbers, which is exactly what we do with the computers. We have some languages we reduce to bits of 0 and 1, and we do everything with that. We represent anything. And of course, the proof of Gödel had this idea of encoding the language using numbers. And the one question which arose is the way that Gödel encodes language, is it correct? Is it something that we can really do? So the three answers to the question are, for me, are the base of the computer science today, because the Gödel recursive function, primitive function, if you think you have just some operation which looks like the way that the processor of the computer works. You have some arrays on number you can project, you can make some easy operation like the sum, and you have, of course, the recursion and the move operator, which allows you to compute everything. The lambda calculus from Church, it's claimed to be the first programming language of this history, at least that's what Wadler says. And it is also, it has been also a paradigm shift, because when mathematicians used to do math, they think in terms of sets, while the lambda calculus changed the shift and think in terms of functions. So mathematics, you have the set, you have functions which are essentially pairs from one set to another. And here the elementary notion is the function, so it's mapping something. And so as I told, Gödel give us the processor, Church give us the programming language, and the Turing machine is the way that you can think as the way in the laptop, the interaction between the RAM and the processor, or at least a non-physical memory and processor. You have something which reads, do some operation, and write. So that's why I wanted to talk about the second problem, and to say that a mathematical question has been the born of computer science. But let's go to the problem, to the 24th, and you can tell me, but Matteo, you told that Hilbert presented 23 problems. What is this 24th? So this 24th problem has been discovered by Thiel. I don't know, it's from Germany, so I'm not sure about the pronunciation. However, it has been discovered 20 years ago on the Hilbert notebook, where he take notes. And there was this question which has not been asked neither at the conference, neither on the paper in which he wrote all the problems. And so we'll read the question, and I will tell you why I think that this question had not been asked. So the 24th problem asks a criterion of simplicity for proof. As often when you heard mathematicians talk, they often say this proof is elegant, is beautiful, is nice. But here the idea of Hilbert was not a matter of taste, was really a simplicity in the term of simple. So what does it mean? I think the idea was to have, what he wrote is to have a process to take one proof and to reduce to a simpler proof. So here still the question of what is a simple proof. Is a shorter proof? Is a proof in which we make less assumption? Is a proof which is self-contained? And how to say, today that we are the habit to think about computer languages, the programming languages, we can have an idea of what can mean a question like this, because we are the habit to formalize informal language. Now, of course, in the 90s, there was at least the mathematical language is mature enough to have some formalism. But if you think of the formalism for proofs, in the 19th, there was not so much. There was not natural deduction. There was not sequent calculus. Then it was very little. There was the Hilbert system. I'm not sure it was already formalized. There was the formalism of Frege. That is quite, I don't know if you ever seen, but it's quite not manageable to write with. So I think that one reason why Hilbert didn't ask this question is because it may seem too vague, or at least it may seem too vague in the 90s. But let's go to see what can mean this proof, this problem. And to do so, I will take two examples. The first one is pretty easy. I think that something similar is done often during the courses of logic. And this is a little theorem. And I say that there are two students enrolled in Rome University which have the same number of hair. And so how to prove it? What I want to show is that there are different proofs of that statement. And one proof is pretty, how to say, brute force proving, is you go and you start to count, you do a census and you go to each student in the University of Rome and counts the number of hairs, and you take a huge book and just write each student the number of hairs. But you can say, okay, this is not a proof because I cannot prove my statement. I should perform the proof to know that the answer is correct. And the other proof is more theoretical. And I know that the students of La Sapienza are more or less 100,000. We have 300 in Roma 2, 400 in Roma 3. And the sum is more than 150,000. And 150,000 is at least what say Wikipedia in French, because I didn't find the page in Italy or in English, is the maximum number of hair that we have. So we have more students than the number of hair, and we can apply the pigeon principle, which I think everybody knows. And we can conclude that there are at least two students with the same number of hair. And I think that we all agree that the two proofs are not the same, because in one, I really have to perform all the steps, while in the one using a pigeon principle, let's say I use a little bit of math, and there is the pigeon principle. So on one side, we are proving that there exists, but we do not show who these two students are. While in the first one, at the end of this mass control operation, we have exactly the two students. So we can have an idea of what does it mean to have two proofs which are not the same. But let's go to some more formal, and let's take a Pythagorean theorem that everybody knows from the elementary school. And I think everybody has studied this proof, which is the, let's say, the original one from Euclid's book of the elements. And the original one, the reason why Euclid wrote his book is to prove the Pythagorean theorem. However, there is this proof that I rather prefer because for me it's easier, it's simpler, because what says that the square on the hypotenuse is the sum on the square of the two sides. And if you want to have fun, there is this website in which you can find 122 different proofs of the Pythagorean theorem. But I claim that they are different, but the real question is, are they different? So can we say that these are different proofs? And how do we say that they are different proofs? So the idea is to find some criterion to decide two proofs are the same. So we have to move to some more formal language, and it's not matter of taste, and try to define some criterion on the formal languages. Now, the possible interpretation and solution. One paper from Titolo, which is the one that discovered the Hilbert problem, and which I suppose is somebody working with automated reasoning, is more or less the following. There is, if you are interested, there is this paper in which they explain this approach of giving a notion of simple proof in terms of fixed formal language, and thinking about how automated prover reason. So you pick a formal language and you write the proof as a code in this language, and you just say that a proof is simpler if it's shorter. And this can be a way to approach the problem. Yes? Questions? No? No. And there are some related problems to this question, and of course there is the idea of proof compression, which if you know a little bit of sequent calculus, you know that when you eliminate the cuts inside the proof, you have a side explosion. So it may be possible that adding some cut in the proof can reduce the size of the proof exponentially. And for example, you can think in that direction about the result of interpolation. And another way to think is to reduce the space of proof search, and by means, for example, of focusing, which you decide that you have to perform some action before others, and it can still think as simpler because you give some constraints of where to apply rules, where to proceed in proof search. However, I see a problem here, and the problem is that different languages may lead to different proofs. I tried to think in terms of programming languages, but I didn't find a nice example. But let's say there are the people from the Finland that have 12 different words for snows. And you can think that to specify one specific type of snow in that language, you have one word, and to specify, for example, in Italian or in English, you need to use 3 or 4 words. And you can think that similarly, some programming languages are more suitable to solve a specific task than the others. So one program in one programming language may be shorter than the same program doing the same task in another programming language, maybe because of the way that the programming language interacts with the memory, or the way that the programming language manage the data structures. So,
Matteo?
Yes.
We have a similar issue with Kolmogorov complexity of computer programs, right? Do you know that?
What do you mean?
The Kolmogorov complexity of a string is the length of the shortest program which can generate that string.
Yes.
And on first sight, it looks like to be heavily language dependent, but then a closer analysis shows that except for an additive constant, it actually doesn't make any difference. And this just reminded me of that. And I was wondering whether there's some connection with it.
It may be. So I'm not too much inside this approach of the problem. So it might be possible that, of course, as you say, that there is no big gap between the two. But
might be, yes, yeah.
But
let's continue. And thank you so much for the talk. I'm really enjoying it up to now.
Okay.
Thank you.
Thank you. And so, as I told, I'm from a different approach, is that before say which one is simpler, let's understand when two proofs are the same. Because they may be of the same length, but they can still be different proofs. And if you have two proofs which are the same length and they are not equal, how can you state which one is the simpler? So let's first understand the problem of proof equivalence. What we know is what we know since Gensen sequent calculus and since when we start to cook at home is that when you have a proof or a cooking recipe, you can swap the order of some process in the proof for some order of some stuff while you're cooking, and the recipe and the proof is still the same. And we know well from Gensen, because the proof of cut elimination from Gensen heavily used the fact that the derivations are considered up to some rule permutation. And for example, this rule, you can pick this application of the rule, and you say that you are just doing this operation which is called par between these two formulas in the sequence. But if you see, there is no reason why you can perform this rule after this tensor. So we can swap the two, and we assume that this is the same proof. And in fact, we consider the same proof when we perform count elimination. When we compose proof, we consider these two proofs are the same. And we can continue, because also this operation, this rule, can be swapped with this one. And in fact, this will only make interact these two, while this rule make interact the B here with the C in the other branch. So we can swap them, and we can still consider this is the same proof. And again, just to be annoying, this rule here, which introduced this par between these two formulas, can we push it up in the derivation until, I don't know, I put it here. And again, I just applied some rule permutation, changing the order of some rule which have no dependency between them. So, is there a way to identify two proofs up to rule permutation? And as the third Hilbert problem, the idea is to associate some invariants such way that I can take one proof and I can associate the invariant, and I know that any equivalent proof will be associated to the same invariant. And so this is the idea. I pass it from this derivation on the left to the derivation on the right, only applying some rule permutation. And what happens that we had the solution before to knowing the problem from using proof nets for at least this little fragment of the logic. And as you see here, what you have, we have the two proofs, and the idea is to associate an invariant to this proof. And so let's start to think of what really matters inside the proof. Of course, the axioms matters, the way that the atoms are related. And the other thing that matters is the way that you compose, you glue together these atoms. So here you can forget whenever you do nothing, but you only keep track of when you introduce some connectives in the formula. And you do the same with the other proof, and then just erase anything. And we pass it from a tree to a proof net, which is a graphical representation of the proof. And the two proofs that we want to be the same are represented by two isomorphic graphs. This is nice. However, we have some bad news. A paper from 2014 tells us that the proofnet syntax works only for this logic. You have a conjunction and a disjunction without weakening contraction. And if you want to have an example of what's going on, if you take the same logic and you add the units, these are two proofnet of associated to two derivations, and you can see that the only thing that I change is that this gate here in one proof is associated to the last one, the last true on the right, and in this other is associated to the second true in the proofnet. And so if you look, what's going on is that the one is connected to this, so this true is connected with this true, which has two associated bottom, which is false, and then is connected with this, which has three associated bottom. While here you have the one, which is connected with this, that now has associated three true values. No, it's a true value is for weakening with four bottoms, three bottom. And then this with three is connected in some sense with this with two. So the two graphs are not isomorphic, and what you can do is forget about these blue edges, but when you forget about the blue edges, you have no more a way to check the correctness of this representation of the proof. So you have to decide, either you have these blue edges which breaks the proof identity. You have two proof nets which represent the same derivation, because doing rule permutation the derivation are the same, or we can keep a correctness criterion to be polynomial, but then we lose the proof identity. And this, we can say that proofnet works, but this approach, but in general, we have no approaches which can work better when we have units or no, units and more. So we have a way to define proof invariance for multiplicative linear logic. We know that we can have with units, and we have a result from 2006, so after the problem, but of course it was a way to give a solution to the 2040 problem, which are the combinatorial proofs. And for who doesn't know, this is a combinatorial proof. The idea is that this is the formula that I want to prove, which I can represent using this graphical representation. There are some results from the 70s, 60s, which says that you can encode formulas with these graphs, which are called cographs, and any cographs encodes a formula. And the idea is to use a purely graphical representation to encode a proof. So as I told you, you can represent the formula as a cograph. This is another cograph of another formula. And we have some results which say that if we had the perfect matching on the vertices of a cograph, which satisfy some topological conditions, And I don't know if you tell more or not, but the idea is that this graph has no cycle of alternating blue and red edges, which has no chords. So for example, do we have a cycle here? No, we have no cycle there. Okay, bad example. However, we are able to characterize graphs which represent linear correct provable formulas. So we have a way to represent proofs by just drawing a graph encoding a formula and some links, which is more or less the same idea of the proof net. In fact, this is another syntax for proof nets. But we also can encode the weakening and contractions which happen in a proof by just some graph homomorphism, which has some additional properties. And so we can put this stuff together, and using a particular proof system, we can show that any formula which is provable admit a combinatorial proof. And in general, we can take a proof in classical logic and we can associate a combinatorial proof. And what we have in the result is that we identify all the rule permutations, but also something more, which is a little detail. And another thing is that this syntax represents cut-free proofs. However, there are some combinatorial proofs which cannot be sequentialized in cut-free proofs. But this is all another story. So the point here is that we have a notion of proof invariance for classical logic, which can be given by these combinatorial proofs, which is another graphical syntax, which extend in some sense the syntax of proof net and allows to recover the full classical logic. And just if you are questioning yourself, can we do something else? And there is a quite nice, not because I brought a lot of them, but there are quite a lot of paper about encoding other logic. So we have combinatorial proof for first order intuitionistic model, some variant of classical logic in which we restrain the weakening contraction. And for example, this, for the people who knows the problem for the proof identity, which is exactly the same that I mentioned for the proof net with units, here the idea was to restrain the proof identity captured by the proof invariance, because you know that we have this mismatch of complexity. I mean, you can either give a syntax in which you can check in polynomial time if the object is corrected, or you can give a syntax which fully captures proof equivalence. But this is not the only possible way to have proof invariance, and just to name few, we have seen that we have sequent calculus. I go back to intuitionistic logic, and these are two combinatorial proofs for the intuitionistic logic. And this is, of course, it's a typed lambda term, which you can think as a proof in natural deduction. And what we have is that, of course, we have the sequent calculus, which we can think without permutation, and we have that combinatorial proofs identify some of the proofs of the sequent calculus. But what happens is that if you go to lambda terms natural deduction, the proofs in natural deduction identify more proofs. In particular, the proof to type this lambda term have at least these two, let's say these two combinatorial proofs can be translated to the same lambda term. And the problem here, at least for me, is that this proof uses 2 times b, while this proof uses only 1 time b. And this information is totally lost in the lambda term syntax. Why is a problem? Is it a problem? you decide, but the fact is that proof assistants as Koch reason the way that the proof theorem works is closer to lambda terms than, of course, sequent calculus or combinatorial proof. And the question is, if I want to verify something, if I want to check a program, does it matter if I use the same resource once or 2 times? You can say, no, I don't care. You can say, yes, I care. But just to know that the current tools usually do not care. And you may be interested in that, especially if you want to, for example, when you pay something online, you have two security checks. One is to give the card number with the code, and the other one is to send the message from your phone. And you say that if you abstract as much as you want, you can think that you have to give 2 authentications. So you see there that the use of 2 authentication is different from just ask 1 authentication. So on the point, if you want to move in some sense in a security mindset,